Hey there. Today we're going to talk about electric potential. The electric potential is an incredibly useful concept, incredibly useful quantity. It's much simpler mathematically than the electric field because it's a scalar, not a vector, and yet it contains all the same information. As far as electrostatics is concerned, electric potential is the thing you want to be using. There are many ways to introduce electric potential. It's already inside of Coulomb's law. Coulomb's law really is the whole story for electrostatics, so you could just deduce it from Coulomb's law. But with an eye toward non-electrostatic situations, I'm going to introduce it by talking about the properties of the electric field when you do a line integral through a closed loop. This is called Faraday's Law, and it's trivial for electrostatics, but it'll be slightly modified when we get away from electrostatics. So let's start with it now. So we'll introduce the electric potential, talk about its physical interpretation in terms of work, computing it using the principle of superposition, start with a point particle and then something more complicated. And finally, we'll talk a bit about equipotential surfaces and, drawing the electric potential. Okay, here we go. The concept of electric potential is based on the following interesting fact. Consider an arbitrary electric field together with an arbitrary closed loop in space. It turns out that in the absence of changing magnetic fields, the line integral of E dot dl around any closed loop is zero. This is a special case of Faraday's law applied to electrostatics. This law is incredibly useful, as we'll see after a slight reformulation. Consider 2 points, A and B, sitting in the electric field, and an arbitrary path gamma 1 connecting them. After we've chosen this path, we can go ahead and compute the integral of E dot dl along the path. We can repeat the process with a different path running from A to B, call it gamma 2, and compare the two integrals that we get. Notice that the difference between these two integrals is the same as a single closed loop integral which runs from A to B along gamma 1 and then back to A along gamma 2. This closed loop integral must be 0. In other words, the integral from A to B of E dot dl is independent of path. Since this line integral is independent of path, there must exist a function v such that the value of the integral is equal to the difference in the endpoint values of this function. Together with a conventional minus sign in front of the integral, this defines the electric potential. Notice that with this definition we're still free to add a constant to the potential. We'll usually choose this constant in such a way that the potential equals 0, infinitely far away from the system we're interested in. The physical meaning of the electric potential is related to the work required to move through an electric field. Consider dragging a test charge Q along this path connecting point A to point B. The test charge will feel an electric force as it moves along the path, and we can calculate the work done by the electric field. Notice that the work done by the electric field is related to the integral of E dot dl along the path. The integral of E dot dl is nothing but minus the difference in potential between points A and points B. Assuming that the charge starts and ends at rest, the external work, that is, the work done by you as you drag the charge along this path, is equal to negative work done by the electric force. So the work done by you is equal to Q times the change in potential. An important computational tool is the principle of superposition. The principle of superposition tells us that the electric potential coming from multiple sources is equal to the sum of the individual potentials coming from each source. In order to make full use of this powerful principle, we'll first calculate the electric potential due to a single point charge. We already know the electric field from the point charge, the usual 1 over r squared law, and to calculate the potential, we just have to do a line integral. Let's put the point charge Q at the origin, and then the electric field points in the radial direction. By spherical symmetry, the electric potential can only depend on the radial coordinate r. Since v at infinity is 0 by convention, v of r is the same as v of r minus v at infinity. This potential difference is easily calculated using our line integral formula. After doing the integral, we find the very useful formula V of r equals 1 over 4 pi epsilon naught times q over r. We can use this formula, together with the principle of superposition, to calculate the electric potential from a more complicated source. Consider a line of charge of length L with uniform charge per unit length lambda. We can quickly and easily use the principle of superposition to find the electric potential a distance r away from the right side of the rod. To do this, imagine breaking up the line charge into a bunch of very, very tiny segments. The potential due to the entire line is the same as the sum of the potentials due to each segment. Let's introduce coordinates on the line to help us keep track of what we're doing. The right side of the line we'll call x equals 0, and the left side of the line will be x equals L. Consider one of our tiny segments which lies somewhere in the middle of the line. These segments are so tiny that they look basically like point charges. That means the formula for the potential of a point charge can be applied to find the potential of an individual segment. Each of these segments has a very, very small width. Let's call it dx. In general, when we have a small quantity associated with a particular segment, it'll be d something. In particular, this tiny segment has a tiny piece of charge. That charge we'll call dq. The potential due to this tiny segment follows the usual point charge formula that we just found. So it's dq over 4 pi epsilon naught times the distance from our segment to the point we're interested in. If this particular segment sits a distance x away from the right side of the rod, then the total distance to our point of interest is x plus r. We can relate the small charge dq to the small length dx. We know that the rod is uniformly charged with charge per unit length lambda. Since this tiny segment has length dx, its tiny charge must be the charge per unit length times dx. So let's plug that in. This is just the potential from one of the segments. Now we have to add up the potential for all of the segments. Each segment is sitting at a different point on the rod, that is, it has a different x-coordinate, and summing up all the potentials is the same as integrating over this x-coordinate. The x-coordinate ranges from 0 on the right side of the rod to L on the left side of the rod, so the total potential V is equal to the integral from 0 to L of this integrand that we've computed. After doing the integral, we find an answer that looks nothing like the answer for a point charge. From this example, we see that if we didn't have the principle of superposition, we would need a very different looking rule for every kind of object. That's why superposition, along with calculus, are very powerful tools. It turns out that knowing the electric potential is enough to give you the electric field. The reason for this is basically mathematical. We know that the difference in potential between 2 points can be calculated as a line integral of the electric field. In the same way that derivatives are like inverses of normal integrals, gradients are like inverses of line integrals. In other words, the electric field is equal to minus the gradient of the potential. In terms of coordinates, it means that the components of the electric field are the negative partial derivatives of the potential. This is a very useful fact, because usually the potential is much easier to compute than the electric field. In addition, the potential is just a single number at each point, whereas the electric field is 3 numbers at each point. Let's illustrate in pictures how the potential encodes all the information of the electric field. Here's a positive charge distribution and the electric field lines emanating from it. On top of this picture, we'll draw the equipotential surfaces. These are curves of constant potential. They are evenly spaced with potential difference V0 from one to the next. A picture of equally spaced equipotential surfaces offers the same information as a picture of electric field lines. Since the electric field is equal to minus the gradient of the potential, we know that the region where the equipotential lines are closer together will have a stronger electric field. That's because in this region, the electric potential is changing more per unit distance. Notice that this is the same as the region with the highest density of electric field lines. Similarly, the region of weak electric field is where the equipotential surfaces are farther apart. If I place a positive test charge Q somewhere in this region, it will feel a force along the electric field lines. In terms of electric potential, this means that the positive test charge will go from a region of high potential to a region of low potential. It's almost like a ball rolling down a hill. A negative test charge, on the other hand, has the opposite behavior. It will go from regions of low potential to regions of high potential. Notice that if I get rid of the electric field lines, we don't lose any information about what's going on in the picture. The equipotential surfaces alone tell the entire story. Alright, that's electric potential. What's next?